All right, last up we have types of solids, types of crystalline solids in their bonding. There are four types of crystalline solids. They are metallic, ionic, molecular, and covalent network, and we'll go through each of them. What I want you to focus on are the types of particles that make up these solids, as well as the attractive forces between these particles. And of course, attractive forces then gives rise to physical properties. So let's start off with metallic solids. The individual particles of a metallic solid are metal atoms. So make a note of that. The individual atoms lose their valence electrons, forming cations. And then the delocalized electrons. So these metal atoms, they don't lose their electrons entirely, but these electrons, the valence electrons of the metal atoms, become delocalized and are able to move around between each of the atoms in that solid. So these delocalized electrons create something called an electron sea, a sea of electrons that acts as a glue holding the atoms together. There's a good picture in your book of a metal. Let me find you a page here. It's on page number 490 at the top. And so we see the blue represents the delocalized electrons. So you have these cations that are all kind of arranged in an orderly fashion. And then you have the valence electrons that are delocalized, able to move around between atoms. And because of these delocalized electrons, metals have certain properties. One of these properties is that they are malleable or bendable. If you look in that same figure, it shows if you were to, smack a metallic solid with a hammer, it would cause the metal to bend. So this is known as malleability, the ability to bend or to be shaped. And so it has to do with the delocalized valence electrons, and nothing separates from one another, as we'll see in another example later on. Metals are also also ductile, again because of these delocalized electrons. Ductile means that if you were to pull on a metallic solid, it would get longer and skinnier. Ductile means can be pulled into wires, so you can make wires out of metallic solids. And once again, because of these delocalized valence electrons, the valence electrons in a metallic solid are able to move around over the entire surface of that metal, which means what then? Means that metals are good conductors of both heat and electricity. So remember, electricity has to do with mobile charged particles. So in a metallic solid, those valence electrons are mobile. They're able to move around, thus giving a metallic solid the ability to conduct electricity as a solid. So no other, or maybe one other example, but this is the primary type of solid that can conduct electricity as a solid. Other other solids cannot conduct electricity as solids. So this is kind of one of the distinguishing features of metallic solids. They also have variable hardness, melting points, and boiling points. I mean, think about that. So metallic bonds are, relatively strong, but their strengths do vary tremendously. Now think about melting point. Some metals have extremely high melting points. Others have pretty low melting points. For example, iron has a melting point is about 1500 degrees Celsius, which is pretty high. Compare that to the melting point of mercury, which is nearly negative 40 Celsius. So we got a big range of melting points. We also have a big range of hardnesses and boiling points. Iron is a very hard metal. Contrast that with sodium. Sodium is soft enough to cut with a knife. So get variable properties for metallic solids. Next up are the ionic solids. It says most salts crystallize as ionic solids. In an ionic solid, the individual particles are ions. You have a whole bunch of cations and anions, a network of cations and anions, and the attractive forces between the particles in this type of solid are ionic bonds. So what's holding the ions together are ionic bonds. Ionic bonds are very strong, and these strong attractive forces then lead to certain properties for this type of solid. They are hard because of these strong attractive forces. However, these are brittle. Ionic solids are brittle, which means if you smack them with a hammer, unlike a metallic solid that will bend, an ionic solid will shatter. If you go back to page 490, it shows you just that, shows you the difference between smacking a metallic solid with a hammer versus an ionic solid with a hammer. And so notice when you smack, this is letter B, if you hit an ionic solid with a hammer, it says force there, you can cause the particles to separate from one another. And that's also being shown in the picture where, you're shearing off pieces of that solid. Those pieces stay held together, but nevertheless, pieces break off from the original substance. Ionic solids, because they have strong attractive forces, have very high melting and boiling points. Sodium chloride, for example, has a melting point of 800 degrees Celsius. Now, we talked earlier in the year about melting point of, say, sodium chloride versus magnesium chloride. So, of course, we go to Coulomb's law to compare relative strengths of electrostatic forces or ionic bonds. And then those differences in the strength of the ionic bonds lead to differences in physical properties such as melting point. Ionic solids are made up of charged particles, but those charged particles in the crystalline solid are not mobile. Therefore, ionic solids are poor conductors of electricity in the solid form. However, ionic solids are good conductors of electricity when melted. So remember, when you melt a solid, the particles are able to slide past one another. So in a molten ionic compound, you have mobile ions, and that liquid is able to conduct electricity. Also, ionic solids conduct electricity when dissolved. So metals conduct electricity as a solid. Metals don't dissolve in water, so they're not going to conduct electricity in solution. Ionic solids don't conduct electricity in the solid form, but do conduct electricity when melted or when in solution. So I'll give you a couple examples, both metallic and ionic solids. Next up, we have molecular solids. This causes a lot of problems with students, so be careful here. A molecular solid, in a molecular solid, the individual particles are molecules, or they could be primarily non-metallic atoms, such as like helium, neon, argon, things like that. Could also be sulfur, could be phosphorus. Those are molecular solids as well. Now, what are the attractive forces between molecules called? These are intermolecular forces. So the force of attraction between the particles in a molecular solid could be dispersion forces, dipole-dipole forces, or hydrogen bonding. Now remember, intermolecular forces are much, much, much weaker than any type of chemical bond, which again gives rise to certain properties for these types of solids. So molecular solids are soft. An example of this would be sulfur, solid sulfur. You can scratch with your fingernails, pretty soft stuff. They have low melting points and boiling points. An example of this would be water. Water is a molecular solid. Its melting point is 0 degrees Celsius. Another example of a molecular solid would be bromine. Bromine is a liquid at room temperature, so that means it must be a solid at some temperature below room temperature. Molecular solids are poor conductors of electricity as a solid, as a liquid, or in solution. They do not conduct electricity because they are not made of charged particles. They're able to move around, and so we get that property. So poor conductors of both heat and electricity. So the fact that they're poor conductors of heat makes them good insulators. So they can't conduct heat. They can hold it in. So good insulators. So we got water, we got sulfur, phosphorus, solid carbon dioxide, sucrose. That's another good example of a molecular solid. Sucrose, table sugar, has a rather low melting point. You could melt sugar right on your stovetop. So going back to sucrose, even though sucrose has hydrogen bonding, the strongest type of, on average, the strongest type of intermolecular force, sugar melts at less than 200 degrees Celsius. So it's not super hot. All right, last one, we have the network solids or covalent solids, or even known as the covalent network solids. Also heard the term macromolecular solids. So these are very important here. Individual particles are usually atoms, usually nonmetallic atoms that are, here's the key, covalently bonded throughout the entire solid. So a whole bunch of particles, mostly nonmetals, and sometimes it's metals, but mostly nonmetal atoms, all held together by covalent bonds. Now you might be thinking, isn't that the case in molecular solids as well? No, within the molecule, there are covalent bonds, but the attractive forces in a molecular solid occur between the molecules, not within. So here we're looking at covalent bonds being the only attractive force between the particles. Covalent bonds are the strongest type of chemical bond, so that gives rise to the observable properties of these solids. Now, it's the difference if the network of covalent bonds is two-dimensional versus three-dimensional. So if the covalent bonds occur throughout the structure three-dimensionally, then this gives rise to solids that are extremely hard. However, if the network of covalent bonds is only two-dimensional, where you create, like in the case of graphite, sheets of carbon atoms, and then those sheets are attracted to other sheets on top or below via dispersion forces, then that creates a slippery substance. So examples of network covalent solids or covalent network solids include what I just mentioned. A different allotrope though of carbon. So graphite is one allotrope of carbon, another is diamond. In diamond we have the three-dimensional network of covalent bonds throughout the entire structure. We can see a picture of this on page 385. Both diamond and graphite are made of just carbon atoms, but how the covalent bonds exist make for very different properties of those substances. Another example listed in your book says quartz or silicon dioxide, where you have silicon and oxygen atoms all covalently bonded to each other throughout the entire structure. So we can see that also, letter C on page 485. Silicon carbide, which is a substance that is commonly used in cutting materials. So if you have abrasive or cutting materials, something that you need to cut through that's really hard, then you could use a saw blade or a drill bit that is covered with silicon carbide. And then another one you need to know is tungsten carbide. Tungsten carbide, another substance used in cutting materials because it is extremely hard. There are others, and so if you were ever given some data, let's say in a test where you have a substance that has an extremely, like very, very, very high melting point, is not a conductor of electricity, either as a solid, doesn't dissolve in solution, then likely that substance is a covalent network solid. So again, just as a comparison, diamond has a melting point of 4,000 degrees Celsius. So get an idea of the attractive force, the strength of attractive forces between the particles in that solid. On page 477 is a very good summary of the types of solids. They're the particles that make them up, the attractive forces between the particles, observable properties, and examples. So please look there. to see everything all in one place and how we can differentiate those types of solids. All right, this concludes our units. Thank you for watching.